Hello, can you hear me? Hello everyone, so thanks for the introduction. I return you the compliment, Elizabeth. I think I don't compete. I'd like to thank the organizers for preparing this very nice seminar, or I don't know how to call it, about sea ice, and I'm very glad that you gave me the opportunity to talk here. I think we are broadcast online. Am I right? So I say hi to my father, who's behind there. And then I'll read my outline to make sure that at least my introduction is correct. Actually, this talk is an answer to a talk by Dirk 3 years ago in Hobart. Do you remember? About how little the complexity of the representation of sea ice matters in global climate models. And I wanted to push it a little bit further and to get a better answer. So that's a private message. Okay, so on the point of view of a model developer or even of a sea ice scientist, it may look somehow desperating how little sensitive climate models seem to be to the representation of sea ice processes. By comparison, atmospheric and oceanic forcing or mean climate and sea ice state have a much more prominent role on the large-scale sea ice uncertainties. Yes?
We're not seeing anything on the screen.
It's always the same thing with me. Winslow had the same experience last time. White slide for my introduction.
Okay.
Yeah, it's to put you in a sea ice mood.
Everything is under control.
Yes. Last time Winslow tried to play with the computer to see what was wrong, but no worries. Okay, so the process driving the phenology of sea ice often prove to light out of the sea ice itself, often in the atmosphere or sometimes in continental setup. And they can be much simpler than one would think at first sight. And with this in mind, why and how should we develop sea ice models? And I will give a few hopefully positive elements of answer. The first one is that it's very good to be able to tell that basic climate statements on sea ice are not sensitive to the complexity of the sea ice representation in models. The second element is that there are major open questions that require better sea ice models, and I will give two of them. And three, we have room to improve our sea ice models and to make them intrinsically better, in particular regarding rheology and reduce empirism of these models. And I will finish by explaining how the European teams involved in the development of NEMO, ocean modeling system, plan to project themselves into a sea ice model of new generation, and I will share that and hopefully get some feedback. Now, those who want to do email or solve Tilches integrals can do that. Okay, so basically the representation of sea ice in climate models follows two major lines. On the left, you see what people have called the Hibbeler two-level model or the monocategory sea ice model. And on the right, you have the multi-category framework or AJAX model. So on the left, you just assume sea ice is made of a single flow with constant thickness and snow depth with given ice concentration. This ice flows drift at a given speed, and on the right you resolve a subgrid distribution of ice properties. So two-level models are quite prominent in CMIP 5, CMIP 6 ensemble of models. I'll give you a brief overview of the equations. So some examples are the MPI model and LIM2 model. It's based on a momentum equation, rheology that connects internal stresses to deformation and ice states, and then a tracer conservation equation for thickness, thickness of the ice, thickness of the snow, concentration, and in the MPI ESM code, I think it's 20 lines of code. So it's the idea behind this model is to keep it very simple. And then the enthalpy formulation is the fourth equation. For such models, it's mostly latent heat, some sensible heat, but very, very minor. For what I call Ajax plus models, such as SICE is, you had an overview on SICE yesterday, but also the LIM3 and gelatos, which are more or less clones, I would say, of these other model. So you now resolve the state variables on ice categories, which is equivalent to resolve the thickness distribution. So you still have one velocity vector, but now you have specific ice fraction, snow, depth, ice thickness. And so the structure is the same, except that here you now have a lot of transport equation for all the thicknesses, all the areas, and the other state variables that you can add, such as salt content or enthalpy. And the enthalpy formulation is now more complicated in these models, where you have sensible heat, latent heat, and brine inclusions in linear or nonlinear formulations. So that's just to give you a little bit of background. Two different models. They are not so different from each other. The main difference is that one resolves the thickness distribution and has more parameterizations. But this is just to give you the very broad ideas. And now my first point will be that ESM's Earth system model sea ice biases seem little sensitive to intermodal differences in the representation of sea ice. So if you look, this is a very classical plot that has been I took the version of my friend François Massonnet, but there are other publications describing that. It's the evolution of the summer minimum extent over the, let's say, 21st century by all the different climate models, and in black you have observations. So huge spread around observations. And so the reflex, the basic reflex is, okay, yeah, to blame sea ice models. Or models are too simple, they don't have enough physics, so we should improve them. But actually, that statement doesn't hold very much. And again, a plot from François Massonnet. When you try to measure the performance of such models based on ice extents and trend. So this is September mean extents, this is trend, and the rectangle here defines what is compatible with observations over the satellite period. And when you analyze which models actually do good, you don't find a link with sea ice model complexity. You have three, let's say, two model levels and three Ajax models that are best in terms of extent, seasonal cycle, trend in extent, and volume for this. So that's first point, little link between sea ice model complexity and model performance. The second point I want to make, it's informal slide from IPSL CM6 preparation. So each plot is a realization of a climate model in the Arctic, September minimum, for different atmospheric tuning and oceanic tuning. So the sea ice model is exactly the same. The sole difference is different atmospheric tuning. Some of these tunings are not so good in terms of atmosphere, but still you can get a sense of what's the sensitivity of the sea ice to the ocean and the atmosphere. It's huge. So that's my second point. Third point is from a publication by Petri Wotila and me this year. Not only me, but that's the important point. Is that the ocean properties and circulation in the Arctic seem fairly insensitive to sea ice physics. So to make these statements, we use the same ocean model with the two different sea ice models that we have. So LIM2 is a two-level model, LIM3 is an Ajax model, And if you compare the sea surface salinity biases between the two models with respect to observations, so this is for LIM 3, this is for LIM 2, do you see a difference? Not really. So ocean model setup exactly the same. CIS model quite different. If you look at the intermodal difference, is much smaller than the difference of model with respect to observations. And if you look at the deep structure of the ocean after 100 years, so these runs are a little bit short, I admit, but also you see not so much difference between both. It's because ice physics, it's growing ice, taking water from the ocean, rejecting salt, transporting ice, and these two models do it similarly.
What's on those plots here, temperature?
I think it's salinity.
For what depth?
It's sea surface salinity. It should, no? Maybe I can check to make sure I didn't take temperature. Sometimes these things happen. But the point is the same. Now I will give you a little bit of new research on sea ice feedbacks. So for those who are familiar, the seasonal cycle and variability of sea ice is affected by mostly two categories of feedbacks. The first category has been mentioned by Elizabeth yesterday. It's the negative feedback that is driven by insulation. Thin ice grows faster than thick ice, so if you melt the ice, the next winter it will grow more, and so that provides a negative feedback. The second set of feedbacks is positive, so you can name it ice albedo feedback. There are several ways to put that together, but the idea is that thin ice melting decreases ice concentration, traps solar radiation, enhances basal melt, which further reduces the ice thickness. So this introduces a positive feedback loop that has been at the base of the SHIBA program. It's a major process. So when you look at these two feedbacks and you try to diagnose them in climate models, this is a job I've done in collaboration with François Massonnet again. And so we attempted to measure these two feedbacks in climate models. I don't detail the technique of measurement, but it's based on regressions of winter volume anomalies for the negative feedbacks. So how much the ice regrows in winter for a given minimum volume. And the positive feedback, we follow the approach of Marika Holland et al. To regress summer area loss versus volume loss. And that gives you an indication of the strength of both feedbacks. And the main results, so this study is in preparation, but the main result, I think, is that the sea ice feedbacks, when you plot them for all climate models, all ensembles, and when you plot them versus mean state, so annual mean volume, they lie nearly on a line. So this is for the negative feedback in meters of ice regrown per minimum volume of ice in meters, and the positive feedback. So you see that they follow a tendency, and so that there is a strong relationship between mean states and feedbacks. So if you split that up in terms of different model complexities, which I think is a really nice plot from François, and you divide between simple, intermediate, and state-of-the-art models, simple being no thickness distribution, zero layer, intermediate models, virtual ITD, zero layer, or state-of-the-art, such as size, gelato, etc. You can't really discriminate between those models in terms of sea ice feedbacks. So these were my 4 points to try to explain that really intrinsically the physics of sea ice at large scale are not really sensitive to model complexity, at least with the sample of sea ice models that we have, which all share some common physics. But voila. And why is this so? So we don't have a final answer yet, but I guess this bold statement summarizes not too badly that the relevant large-scale CI physics often go beyond intermodal differences. And I give you a few examples. For example, if you look at the question of when does Arctic multi-year ice disappears, it all appears related to mean state. I put two plots from two recent publications. I guess you will hear about this tomorrow. But when you look at the problem of multi-year ice disappearance, it appears that the sea ice extent linearly responds to forcing perturbation. So if you get the mean state for now correct, then you get the correct answer for the n. If you look at another thing I've done recently, if you look at ice seasonality, so if you look at the date of ice retreat and the date of ice freeze-up, this is the median over the Arctic seasonal ice zone. In CMIP and in the Sempner zero layer, very simple model. If you look at the tendencies over the future, all models are fairly similar in how they simulate seasonality. So they all tell you that freeze-up date will retreat will offset faster than the retreat date. And it's true both for CMIP and simple models. And when you look into the explanation required for that, you end up with a very simple explanation that is related to the upper ocean budget. Is that the date of freeze-up, the change in date of freeze-up divided by the change in ice retreat is related to the ratio of the heat input to the ice-free ocean divided by the heat loss over the summer ice-free ocean, and this ratio is pretty much solar heat divided by long-wave emission. And it's always larger than 1. So freeze-up date offsets faster than retreat date. So first point, we had a dependence on mean state. Here sea ice will respond to the upper ocean physics. And I think there are other examples. I picked up one example from a work of Ian that I heard many times of when I was in Seattle, is that you have, if you look at change in Arctic winter versus summer sea ice extent, you have a first order control by the muting effect of continents. So nothing to do with sea ice physics. The main driver was the fact that there are continents, and that determines the change in Arctic winter versus summer sea ice extent. I've seen, I didn't put the citation, it's Bathiani et al. Here, but they looked into the abrupt winter disparition of sea ice into the 22nd century, and the driver here was the first order control by the asymmetry of growing ice and melting ice. The fact that to grow ice, you just need to grow a little bit of thickness, and to melt ice, you need to melt a lot of different thicknesses. I don't want you to remember all the small details here, but pretty much the explanation for the large-scale behavior of sea ice here and there to say when and where sea ice is outside of the sea ice. So now, why improving sea ice models? As a sea ice scientist, not being desperate is not obvious. So I decided to call my mentors. And one of my mentors is actually Isaac Newton. So I gave a phone call to Isaac, and he gave me an answer. I had to translate it from Latin. He says, excellent, that basic climate statements on sea ice are not sensitive to the complexity of the sea ice representation in models. So it's good to have complex models, because if we have complex models and they tell the same as simple ones, it means that we have understood something. Maybe it's not enough, so I called Jesus, which is another of my mentors. And so Jesus told me, oh, don't lose hope. There are other sea ice problems that need you and are also quite interesting. And the third person I tried to call, was Jeff Buckley, to have some musical insight, but I dialed the wrong number. And I got instead Jeff Ridley. And Jeffrey Lee told me, oh, use size, not lim, it's the best model. Okay, so now more serious answers about why improving CI's model. First thing I think is we are doing fundamental research. That's an argument from Dirk. It's fun and intellectually rewarding to understand. Another statement I think we can make is that maintaining the existing systems actually require development because the ocean and the atmosphere evolve and we have to adapt to that. So we have to at least to work on something. I think the third point was made by Isaac Newton. Target a best model reinforces confidence and reduce climate uncertainties. But what I want to concentrate on is that some science questions may benefit from an improved description of sea ice, especially at regional scales and for sea ice biogeochemistry. So regional scales, I think the problem of polynyas and deep water formation is one that requires a lot of attention. So it's a little bit loose, but I think we know that sea ice models presently hardly capture the ice arch-driven fast ice. So fast ice is the ice that is attached to the coast. You have some of it in the Arctic, but you also have a lot of it along the Antarctic continent. And recent research has shown that land-fast ice is an essential element for the formation of most Antarctic coastal polynyas. That's something I've heard from Rob Masson, but I think the Japanese guys also have worked on that. And I found a map. I know these polynya maps are debatable, but take them as they are. In red you have polynyas, and in blue you have fast ice as retrieved from satellites. And you see that actually polynyas always form on the lee of fast ice on the Antarctic coast. So there is a relation between fast ice and polynyas, and our models, we know they don't do it well. Another point is that no Earth system models today has Antarctic deep water forming at the correct location. And it's in relation to an imprecise representation of polynyas. This is the wrong slide, or my slide disappeared. Too bad, it's okay. So I wanted to show you that ESMs convect in the Weddell Sea, typically a lot, to compensate for the absence of polynyas. So I have no support, but it's okay. If you look now at regional sea ice models, we have a regional configuration around Svalbard, and this is the movie that's about to come. It's very complicated to correctly open polynyas with current models. So this is the wax and wane of sea ice over a given year. I forgot which one. It's from my colleague Clément Rousset. And so here you see this is the Storfjorden polynya, and it doesn't open pretty much in the model. We've tried many different strategies to open it. It opens very late in the season, but not during winter, and it's because we actually don't resolve the fast ice here. Here and there you have some arching and some fast ice that forms in reality. You can see that from satellites, and our sea ice is instead viscously drifting and prevents the closing of the polynya. That's the diagnostic from Clément. So we have to reinforce that, but we don't have enough deep water formation, so it's really suspicious. Just to remind those who are not aware that Antarctic polynyas are supposed to form 30 to 40% of the world ocean deep water. So it's a huge amount of cold and saline water that is formed there. So it's super important for the ocean circulation, and we don't get that for the good reasons in present climate models, probably related to the fact that we don't resolve fast ice. There are also other elements, of course, slope currents, we don't do it well, the glaciers, we don't do it well, but probably there is something to understand there. And hopefully with these improved rheologies that we have seen yesterday, I think we get better sense of arching in there, and maybe we'll get better polymers. So I think that's a very fair target to keep in mind when doing sea ice modeling, that we don't really understand the source of deep water, and these are linked to polymias, which are sea ice phenomena. Second point is sea ice biogeochemistry. So I'm not sure sea ice biogeochemistry is climate relevant. That's not the claim, but it's interesting in itself because sea ice is one of the largest biomes on Earth. It covers the Europe and United States together, you said yesterday. North America plus Europe. So imagine all this covered with ice algae. It's not a huge amount of carbon, but still it's important to understand that and the role in ecosystems. And the current models, at least the one we have, I think you have a recent publication from Duarte. I had no time to read it yet, but in our model, we are unable to match nutrient supply from brine drainage and the nutrient demand from growing algae. I will give you a short sense of that. So these crosses are observations of biomass, so the total amount of biomass that was observed at a given site, and we are simulating that site with different versions of our 1D model. So this is biomass and this is nutrients, so nutrients is the food that they are made of. And so any attempt we have made to simulate the observed biomass has been a failure. So we've tried to play on the ecosystem model complexity, the light limitation function, some crazy processes like adsorption of nutrients in biofilm, decoupling nitrogen, carbon, phosphorus. We've tried two different brine dynamic schemes, advective and diffusive. It doesn't help. So after having done that, we went back to the stupid back of the envelope calculation, and actually the nutrient demand from that site from Antarctic land fast ice exceeds by 5 to 10 times the nutrient demand. Yes, so nutrient demand from that site requires from 2 to 5 10 to minus 7 meters per second of brine vertical velocity, and the models we have predict a maximum of this. And it's independent on the gravity drainage parameterization. We can't help it. Actually, the diffusive parameterization is a little bit more efficient. I don't claim it's better. Actually, it's not. But still. So we need to understand what happens. And here we don't really know what's missing. So that's an open question. I leave it like that. So that was for the why. So now it's a little bit of advertisement here, but I think it's a good place to do it. So we are in the stage of planning the new evaluation of all sea ice models in NEMO. So what is NEMO? NEMO is the French, UK, Italian ocean sea ice modeling system. So it's original in the fact that it combines different institutions at different places. French CNRS, Italy, UK Met Office, and NERC. So it's a big player in ESM research today in Europe. It's used in several ESMs. And so until this year we had 4 sea ice models. So you can tell that this is a positive situation because you have a lot of diversity in there. So we had 4 sea ice models, but it was a nightmare for maintenance, and our engineers started to get mad because they had to cope with 4 sea ice models. So I don't know if you imagine, but in terms of code maintenance, that's terrible. Every time you modify something here, you have to make sure that your 4 CIS models are working. So you use, it's a lot of waste of manpower. Arguably, there is no major difference between these CIS models, and it means many duplications. So there was an institutional push to put together a CIS working group to improve efficiency, to reduce duplication in here. And so our mandate was to identify and reduce duplication and design a long-term strategy. And so our recommendation that was finally accepted is that we will do one unique CIS model for NEMO, and we arrogantly call it European CIS models, because of course these 3 countries are the entire Europe. Okay, so the strategy, there is a poster by Ed Blockley, who's there. There is a poster over there that you can go and you can discuss if you're interested. But this is where what we have in mind. In terms of transition from present state to future state. So now we prepare the code and open the first branch. This has been done actually. And there is this critical transition phase where all the groups doing different CIS models retrieve their initial capabilities. So that means a lot of merging of everything that is here and there. And then we have to evaluate the new model. Yes. But probably the more interesting part is that the future evolution will be collectively discussed. So it will be a collective process. And we plan a workshop in early 2019. We may contact some of you to come and chat with us to get your opinion on what you think is a worthwhile evolution, where we should put our resources to make progress. And that would mean that we could start working on new things beyond 2019. I think I have 5 minutes to give you a little bit of how this future evolution could look like. What do we mean by a better model? And I invite you to rewatch the excellent Elizabeth talk yesterday. She had plenty of items where I was like, yeah. These are mine, but that needs to be discussed. So the first thing that a good CIS model needs is to be robust. Robust in terms of stability, numerical stability, and conservation. So if you don't conserve, you are not going to do climate science. And you need to conserve very well because you have to be prepared for very long integrations. So if you lose a little bit of water every year, then sea level, that's a problem. Second point is efficient numerics. So this I picked up from Elizabeth, and means cheap in terms of CPU and precise. And then after comes the better physics. And so improving physics means probably we should target less empirical and less scale dependent. And there are lots of options available at the moment. We could also try to increase the span of our models. Ideally, our CIS models should do everything, all scales, but in practice we have to make choices. And in NEMO, our limitation is 1 kilometer resolution, I think. 1 kilometer effective resolution. I think also something that could be interesting, that's already in size, I've noticed that to maintain several levels of complexity in the models. Maintain monocategory, multi-category, and all these various levels of complexity, because that gives a lot of scientific possibilities. And also we have to make sure that if we add more processes, we also try to maintain a simple system. Because a big system means a lot of maintenance and a lot of engineer work at the expense of scientific activities. So in terms of potential evolution, I think the biggest thing, as everyone knows, is ice dynamics. So we are all based on continuum approach and EVP rheology. What the future looks like is in between these different rheologies. Continuum approach, discrete flows. I guess we have to discuss that. And also the old versus new rheologies. There are, I think EAP is already in size, but we have improved VP solvers, and we have all these elasto-brittle family of rheologies. And also the fact that you can have Eulerian and Lagrangian meshes. And here I will please Pierre Rampal, who could not show his movie yesterday, but I think that's very encouraging to see. Can I play that? Yes. Encouraging that CIS models, some CIS models are already able to have very nice plate tectonics, new physics. You see here the fast ice in the Kara Sea. I was impressed how they can simulate fractures. I think this is one of the promising approaches. I don't claim this is the way to go for us, but I think the new rheologies are really a way, easy way to improve our models. In terms of thermodynamics, I think there is probably less room. In terms of pure thermodynamics, I think over the last years, the enthalpy formulations have been worked on, and empirical and the desalination schemes have been progressed, and we can incorporate that progress. As far as melt ponds are concerned, we had no melt ponds. We had simple snow. Probably we moved to that. In terms of radiative transfer, also we need to progress. Yeah, okay. So I think I will skip. I got extra material to show, but I will show it to the persons I wanted to show. To let you some time to drink coffee. But yes, so that was about generalized enthalpy formulation, intercomparing brine dynamic schemes, work by Max Thomas in East Anglia compared to observations. Yes, I think I made my points here. So the details of CIS models usually do not really matter for large-scale climate science questions. And this is because large-scale CIS processes are probably simpler than intermodal differences. But still, it's very nice to see that when both complex and simple models agree, we improve our confidence in these models. But still, we can expand the scope of our CIS models to regional and impact studies, which require better models. Include more processes, if possible, less empirical, more robust. And I invite you to feedback on us as far as you see the evolution of future CIS models. Thanks for your attention.
Can I just make a quick note? When people are taking questions, can they please stand up and speak loudly? Because people at the back can't hear. And probably the people online can't hear either. So.
Yeah, so I just wanted to make a sort of high-level point, which is that when you have this part one that you were talking about, where you have models that sort of are indistinguishable depending on complexity, there's two ways of looking at that, right? One of them is to be comforted by the fact that it doesn't matter, and one of them is to be discouraged by the fact that it doesn't matter. And I'm of the discouraged side, because it means that there's a lot of interdependency. And I would suggest a lot of that comes from tuning to very specific metrics, like the September sea ice minimum extent, which now they all do a pretty good job at estimating that with each other, but we're ignoring a whole bunch of other things that should be used to actually validate these models. And the models that actually the sea ice models are dependent on, the atmospheric and ocean models, are constrained against a lot different and more varied types of observations.
Actually, I would say that it's not only the September minimum CIS extent, it's more than that. Groups tend to tune the volume, as far as I understand.
We don't have a good observations of volume.
I'd say the problem is that all models are tuned to Shiba or AJ.
Yeah.
More
So maybe we, yeah, so you know, we've been
Actually,
talking-
if you look a little bit more into this feedback thing I've mentioned, I didn't give all the elements, but it seems that feedbacks are dependent on mean states, and feedbacks determine a lot of internal variability, trends, etc. So I'm not sure yet we miss something.
Yeah. So, following,
Islav, sorry. Go ahead.
should I say my name?
Yes.
Wisław Masłowski.
Just speak loudly so people can hear.
Following on that comment and your presentation of the no sensitivity, I think that, to me at least, from my experience, what it says is just we have much bigger errors in those models that whether cancel or not each other, but they're much bigger than corrections or improvements we get by improved CIS models.
Mm-hmm. Yeah, I think it's a nice way to reward what I wanted to say.
So, go ahead.
I just wanted to go to the beginning of your talk because you mentioned that model of Hibbeler and model of object is very similar. But basically one model is viscous plastic and another is elastoplastic.
Okay, sorry.
They are very different. And but until your example are related mostly to thermodynamics, maybe it is not very important. But if you would be more interested in some mechanical processes, so of course it became more important. And I want to give one example, drift around Kupan Island. I compared drift modeled by NEMO model in Russia. They use like based Hibbeler model. And the drift is very different from drift of ice trackers. Because around Kupan Island you have the range of compressed ice which influence over several tens of kilometers drift. So therefore, I think that if you look into mechanical properties, you will find that rheology is important.
Yes, I apologize. I call Ajax models actually what we mean as thickness distribution models. And I wanted to call them like that to acknowledge the fact that this thickness distribution approach comes from there. But I didn't mean that we are using the elastic plastic rheology of Kuhn et al., which no one has ever did in climate models. So first, and second, what you mentioned, I think it's a problem at small scales, and I didn't tell at all that different CIS models do the same at small scales. I spoke of climate scales.
But you have 1 cell, 1 kilometer, you said. It's possible to have half of kilometers, but if you have a difference at scale of several tens of kilometers, and it is visible on the real ice trajectory, so then that's important.
If you look at the elastobrittle solution compared to the viscous plastic solution, at small scales they are fairly different, and I don't contest that. I think my point was really to look at very large scale questions. When CIS will disappear, does that question, the answer to that question depends on the complexity of the model used. That's
our scope, I think. That's enough.
But at small scales, I totally buy your point.
Let's take one more question from David.
Yeah, was a very nice presentation, but I think I do not agree to your first two conclusions. You showed that it doesn't, whether you include a more complex CIS model, it doesn't improve the climate scenario so far, or the models from what you could test it. But I don't think you can conclude from that the physics and the CIS model don't matter, because there are several explanations for why this is the case. And in my opinion, the main thing it showed was more the opposite. It shows that we do not make enough use of the additional physics we have. For example, for the ice thickness distribution, which gives us a lot more opportunities in the model to simulate the change in the ice thickness room, but we are not good enough. The model is, we don't use the potential of that in a way that we actually improve the model. So there is the need to improve that, and there are some problems with it. And when we improve that, we could have quite a big impact on the future stuff. And there's another problem, of course, a lot depends on tuning of the CIS model. There's a huge tuning way, and there are only a limited amount of observations which have been used by all climate models.
I completely buy your point, and I'm a modeler as well, and I would like to believe that. But with the evidence I have in my hand, I'm forced to conclude. I have no other elements. I couldn't find a study where they found where the complexity of sea ice model representation would matter for climate questions. And yes.
Okay, so I think we'll cut off questions right there. I would like to add one comment on this conversation because I do have pretty strong opinions about it. But
I wanted to represent one very
yes,
specific opinion. It doesn't
and
mean
I think that you're right on. And the last thing that you just said, 4 climate questions. That's the key. The complexity that you need depends on the question that you want to answer. And so we've added a bunch of biogeochemistry into the model. And like Martin said, that might not be important for climate. We're still trying to decide whether it is or not through aerosols and clouds and all that kind of stuff. But for sea ice physics, probably not that important. It's a lower order process. But we still need it to answer a different question besides the climate question. So that's how I feel about it. Thank you very much. And we'll come back at